Welcome to today's webinar. This is the January 2021 webinar for the NGSS ESS Working Group. Our webinar today is entitled Using an American Museum of Natural History Teaching Case to Analyze and Interpret Patterns of Ice Mass Loss in Greenland and Antarctica. And in case we aren't all familiar with the Zoom tools, there they are. I know we're all Zoom experts. We can find those things with one hand tied behind our backs and a blindfold on. So I'm going to go ahead and go to the next slide, please. Actually, you can, yeah, perfect. So my name is Aida Awad. I'm the past president of NAGT. Typically, along with me on this webinar are Ed Robeck and Missy Holzer. They are both off doing other events today. Mitchell Awalt is in the background for us running the tech. Thank you, Mitch, for being here. Next slide, please. For today's webinar, we have one presenter, and that's Dave Randall. We'll also have time at the end for a little bit of discussion and Q&A, and we'll share with you the post-webinar survey link at that time. During the course of the webinar, please do make sure that you're typing not just questions, but ideas and thoughts into the chat box. That's what it's there for. It's not called a question box, it's called a chat box. So please engage with us in the chat box as we go through. Next slide, please. This is a monthly webinar series. We have our February webinar, which registration will be opening tomorrow for. We'll be sending out an announcement of that. That webinar will be on February 11th at 4 p.m. Eastern, and it will be presented by members of the Soil Society of America. It is entitled Soil Biology, Chemistry, and Physics, Oh My. And we always invite you to visit the AGI YouTube channel, where the entire playlist of all now almost 8 years of webinars are housed. So please go there and visit our previous webinars. Next slide, please. Going to, at this point, go ahead and turn it over to Dave Randall for today's presentation. Please remember, as we're going through the webinar, to add your thoughts and ideas into the chat box. Dave, the floor is yours.
All right, thank you. Hi, everybody. It's a pleasure to be here. I'm going to share with you today an example of one of the resources that we have at the American Museum of Natural History in New York. It's called the Teaching Case. In this particular one, we're going to use to look at ice mass loss in Greenland and Antarctica, and it's based on NASA's GRACE mission. The teaching cases, we have several of them, and I'll quickly run through the examples, so in case you're interested and you teach something other than earth science. But basically, this is a response to lots of sort of secondary data, so data that students haven't collected being available on the web. And we're sort of looking at the problem of having students analyze this data and not really having a context for where that data came from. And so we've kind of refined this model of, it's a 4-part model, 5 parts really, including the data analysis of combining readings and videos, and then a data analysis activity to kind of help the kids see the story, or follow the scientists really through the story and kind of look at the questions that they're trying to answer. So each of the teaching cases is a little bit different, but in this case, we have an introduction that sort of sets the stage. After that, we would stop and do an activity, which I'll explain in a second. And then we're going to do another reading and part of the video so that you see how the data is collected. Then we would do a data analysis activity. And then so the kids can work with the data that the scientists collected and come up with their own conclusions before they move into part 3, which is a reading that kind of explains from the scientist's perspective what they found, in their analysis of that data. And then the last piece is, more broader implications of the data. And so we follow this model, and I'll take you through, we're going to dip our toe quickly into the GRACE data, but we have one for looking at blue whale data. The data here are tracking tags that some scientists from Stanford put on the back of the whale. So you actually get video of the whale diving from looking, kind of towards the tail and towards the head, and speed and depth and all kinds of stuff. So it's really kind of a cool data that they collect. We have one that uses phylogenetic trees to look at the origin of methicillin-resistant Staphylococcus bacteria. We have one that uses IRIS data to look at earthquake risk in Bangladesh. So there's a lot of social implications there of this incredibly poor country with not a lot of resources getting kind of bracing for an inevitable huge earthquake. We have one that looks at zebra mussel data. So the Carey Institute up in Kingston, New York, about an hour's drive north of New York City, has been collecting data on the Hudson River for several years, and we have a bunch of data before the zebra mussels invaded the river, and then after. So it's a cool kind of before and after, stability and change or cause and effect kind of case study. And then the one that we're going to look at today looks at the GRACE mission, and it's how it can use pretty ingeniously track changes in water on the Earth. So really quickly, so what I'm going to show you in the next 40 minutes, we would spend at least a day in a teacher professional development session, and teachers would probably spend multiple days going through this with their kids in a class. But the basic goals are, from a science learning perspective, is to become familiar with the use of satellite data for studying the climate and to look at some of the implications of climate change. And, as a teacher, I would love for you to kind of dip your toe into this teaching case model and maybe explore some of the others. And then to look at really briefly at some strategies for analyzing and interpreting data. And sort of where this is going to fit in, in the NGSS. So probably the best cross-cutting concept for what we're going to be looking at today would be stability and change, the science and engineering practices, probably analyzing and interpreting data, and a little bit of math and computational thinking. And then in terms of our disciplinary core ideas, this kind of fits in the Earth and human activity bucket under the climate part of that. So I'll give you the URL for this a little bit later, but the GRACE teaching case is kind of all encapsulated on a page that looks something like this. And under this tab right here, we would come to our first curriculum piece, which is a reading. The readings come in two flavors. This is a quick example of the teacher version, but we also have a middle school sort of Lexile level for 7th, 8th grade. And it's organized a little differently. It's single column. It's a little bit shorter. And it's designed so that you can use, if you use literacy strategies in your classroom, there's plenty of space for sort of annotating on the sides. And we don't have time for me to have you read this, but what I would have teachers do, and teachers would have their students do as they go through here, is kind of look for some of the definitions that are presented in here to kind of make sure that they're gathering them. And so this is what's covered. It's a little bit of front loading, but this is what's covered in this first essay. And I'll give you a second in case you're not familiar with any of these terms. The big one here is this idea of ice sheets. So these huge masses of ice, of land ice, and the only places we have them on our planet are Greenland and Antarctica. And then the other idea is just like the composition of water on Earth, and the fact that it's mostly salt water, and then of the fresh water, most of it's underground, or a lot of it's underground, most of it's ice, and then there's just a thin slice of the stuff that we can actually use as humans. So any change in that, could present issues. So I would have you read this, and then we would spend some time. I usually pull out a whiteboard and then look at these last two things here. So when we think about what data should scientists collect in order to investigate Greenland and the Antarctic ice sheets, and then what methods do you think they should use? And so I usually make a T-chart one side for the data and one side for the method. We just do a brainstorm for a few minutes. And they come up with lots of ways. Sometimes, even though they know that it's about grace, they don't mention satellites. Sometimes they do. And then that would lead us into part 2, which introduces the grace satellites and how things work. There's a reading there, which of course we're not going to have time for, but there is also part of a video that I'm going to share with you to kind of introduce the GRACE mission to us all. And it's right here. So this is part of a longer video. I'm just going to play the first 3 minutes of it.
Of the universe. Gravity is one of the fundamental forces of the universe, and it's connected with mass. Anything that has mass has gravity.
Dave, we're not seeing your screen right now.
Stopped. Oh, we tend to think of the weight of the Earth as.
Is that better?
Yes, looks like it's going to be.
Okay, let me start this over again.
Gravity is one of the fundamental forces of the universe, and it's connected with mass. Anything that has mass has gravity. We tend to think of the weight of the Earth as being entirely rocks and magma deep in the Earth. But actually, on the surface of the Earth, as you look around, you see the atmosphere and you see the ocean and you see snowfields and polar ice caps. All of those things have mass too. But those things change much more frequently. So what we realized is if we could design a mission that was accurate enough to observe those small changes, we could actually watch the polar ice caps melt. We could measure polar ice mass loss. We could even measure how much water is in the ground after it rains. And that led us to come up with the GRACE mission. Deep in the Earth, or even on the surface of the Earth, the way mass is distributed with mountains and trenches and all kinds of things is slightly different, slightly non-uniform. So as you were to walk around the Earth, you'd actually sense more or less gravity. You actually weigh a little bit more, a little bit less on different parts of the Earth. Isaac Newton taught us that the amount of mass that I'm standing on top of affects the gravity where I'm standing. So the rate at which this apple comes down is a function of how much mass is below me on the Earth. So no matter where you are, what's below you will be different. So gravity will be different, and so the apple will drop at a different rate. The orbit of a satellite is highly dependent upon the gravity field of the planet that it's orbiting. So what we wanted to do was put up a satellite whose orbit we could measure incredibly accurately. The best way to do that was to observe one satellite with another satellite. So the satellites are sort of chasing each other, pole to pole, flying around the Earth. And as the first one comes up, for example, on a mountain, it feels that mountain first. So it starts to get pulled toward the mountain. But the second one isn't quite there yet, so the satellites tend to sort of drift apart. Then, of course, as they're leaving the mountain, the second one is still feeling the effect of the mountain. So they come together again. And that sort of dance that the two satellites do as they go around the Earth is what tells us what the gravity field underneath them was. Now, in addition to that, the gravity field is also changing every day, every week, every month, because water is moving all around the Earth and it's raining here or the polar ice cap is melting. So water is the primary thing that's changing. But what scientists really want to understand is not just what happens across 1 year. They want to really see that play out over many years, over decades, to try to understand what's really happening in the climate system.
So I always ask the trick question here to the teachers, like of what the data that the satellites are collecting is, because we kind of get into this data and inference thing. And a lot of them say, it's the gravity field, it's the amount of ice, and technically it's just the distance between those two satellites. And then they use that to make the inference about the changing, water down below it. And it's pretty incredible. So these satellites, they started collecting data in late 2002, and they lasted until I think they finally fell out of orbit and were shut down, and then fell out of orbit in 2017, and they actually were able to launch a follow-on mission. So there's a little break. If you look at our website, the data I'm going to show you, there's no break in the data. But if you go to NASA's data, and I'll show you how to get there as well, there's a little bit of break in the data between the two satellite missions. But it's pretty ingenious. And so when you think about it, those two satellites, the first mission anyway, they would fly about 130 kilometers apart. And that change that he's talking about is millimeters. So it's not like big changes. It's just like, kind of millimeter level changes that they're able to, do fancy math and figure out, the gravity field down below. And then as they go, so they do one orbit every 90 minutes, and it takes them about a month to make a complete gravity map of the Earth. And so the thing that changes on a month-to-month basis is on the surface of the planet is going to be water. So water is pretty heavy, it has gravity, so it actually affects the way these satellites orbit. And so they're able to make a map that I'd like you to look at.
Dave, I'm going to interrupt you just for a second.
Yep.
We have a question in the chat box that I want to make sure that we touch on before we go further, so we don't have any concerns. There's one question about deciding on the speed of the satellite. Is that controlled by someone from the ground, or is that happening because of the gravity field?
Ooh, you'd have to talk to a NASA JPL person for that one. I think a 90-minute orbit is a fairly standard orbit for where these guys are. It probably relates to maintaining a pretty consistent altitude, but that one's a little bit out of my reach. But it's the characteristics of the orbit. So I don't know. I'm sure it's determined by the physics of keeping them in orbit like that. That was totally unsatisfactory, I know, but.
No, actually, it's very good.
So I'm going to let me show you what I'm going to send you first. So on this, so the resources are here. So I'll give you the link to this page in a bit. But in the second tab would take you here. And this is, I'm going to actually, we're going to go into groups in a second. And I want you to spend a little bit of time kind of playing with this interactive and kind of just talking about the patterns that you see. So what are the patterns that you see that you recognize over the course? And unfortunately, this is not, it goes from 2003 to 2009, and it's not marked off according to year, unfortunately. But I think you can probably tell by looking at patterns that you might see in the tropics, kind of when the seasons are changing. So what this presents is this idea of a water storage anomaly, and basic. And so this is a tough concept for kids sometimes. But basically, if it's red, it's drier than the average for that area. Okay, and if it's blue, it's wetter than the average for that area. And the average is from over this whole data set. So if we were to add more data to this visualization, the zero line would change. So it's basically, it shows you the change, and it's specific to each area. So it's not over the whole planet. So kind of look for trends that you might see. And then if you have time, you can kind of pop down here, and we're going to be looking at Greenland and Antarctica. So you might want to pop in, and we can zoom in and get some information on Antarctica. And then so you just push the button, and it'll kind of proceed through the data. And so you get the color changes over here, and you get a graph of water storage here. And then you can get the same thing for Greenland. And we also have the Central Valley of California, Austria, India, the Lena Basin of Russia. We're not going to address those today. And the I have, if you're really interested in those, email me, because we have some of the great scientists sort of supplied us with some of the ways to look at that data, but it's actually pretty complicated. Greenland and Antarctica, we're just looking at ice storage, changes in ice storage. And with these guys, if you want to look at groundwater and everything, you're dealing with evapotranspiration and all kinds of stuff like that. So the equations are more complicated, but you can do the analysis if you're up for it and your kids are up for it. So we're going to send you into groups of like 4 or 5. So introduce yourselves really quickly. You may want to have one person in your group share the screen, and then kind of look through this. I'm going to place this URL in the chat. So you want to grab that before you go into the chat, because I don't think that the chat follows you into the group necessarily. And basically you're just looking for trends, patterns, noticings. Right, so there's the data interactive. So I'm going to grab that, and let's go till 4:30. So I'll give you about 8 minutes to do this. And so Mitchell will invite you into a group, and as soon as you grab that URL, go in. So you're looking for patterns. So what are the patterns that you see in that water storage anomaly visualization? I'm seeing the question now. Henri, is that you? How do you decide to reduce the speed of the satellite? I think they just fall out of orbit. I think they just fall. I mean, you know, an orbit is a fall anyway. And I think
the idea was when you show the images, the 2 satellites at the moment, one was getting a faster speed and the other one wait. So how could you in the space control the speed when the one was over the land and the other one just wait?
So you don't control the speed, but that's actually the data that they collect. So if let's say one satellite is getting close to the Himalayas, right? So that gravity would pull that satellite, would affect that first satellite before it affected the other one. So that pulls them apart slightly. And so that's what they record as the data, and then they use that, the changes in that. So then, you know, as it goes across, and then the other satellite approaches the Himalayas and would be more affected by that. So depending on the mass of the Earth and the water and the ice below the satellites, that causes them to kind of slightly, the distance between them changes ever so slightly.
Okay.
And that's where they get the calculations for the mass below, the gravity below.
I did not catch that first.
Yeah. It's pretty cool. It's pretty ingenious. Yeah.
Thank you.
So anybody want to share really quickly anything that they noticed? Looking at the water.
I have another question.
Sure.
When you show the map, we see that the northern part of South America is drier than the desert in Africa. That surprised me.
Well, be careful, because the color is specific to the location on the map, right? So it's whether it's drier or wetter than usual for that location. Okay, so let me share my screen again.
So I was in the group with Henri and we were talking about this, and one comment I would make is where it says below that the anomaly is the difference from the average, maybe put a note in there that it's the average for that specific location, not, you know, global average, and because it is not drier, right? It just has a larger variability. Right.
So right here, like, yeah, let me share my screen. So you see, like, you know, this rainforest area is showing it as red. It just means that's drier than average for that area during the course of the data. So yeah, it's. I mean, the anomaly is really tricky for kids, but yeah, we make sure we clarify that really. I tried to clarify it for you guys, and when I'm working with teachers and students, we actually spend some time on that to make sure that they're interpreting that correctly. Any other questions really quick before we move on? We're running out of time fast, but.
Is a
Our group
centimeters
had quick
equivalent?
question.
Oh, go ahead.
Okay, I was in group 4, and we were just wondering, for instance, like Greenland, we were kind of watching Greenland for a little bit, and we were wondering if during the times when it is showing it being drier than average, is that total moisture, so including both ice and liquid water, or is it just looking at liquid water?
No, it's going to pick up the total, it actually picks up the change in gravity. Okay.
Okay.
And so that's interpreted. The only thing that's really changing on a scale from month to month on the Earth is water storage. So in Greenland, it's going to be ice.
Okay, all right.
So what did you guys notice, in the Greenland?
It got darker over time. Like the drier than average seemed to be increasing over time.
Right. So rather than some places like the rainforests where you had a seasonal flip flop, right? So it went blue and then it went red, and then it went blue and went red. Greenland sort of started out blue, and then it progressively got red. So what does that mean? And so what we're going to do is I'm going to show you another way to look at the data that's going to allow you to zero in on that a little bit. We're not going to, unfortunately, have a lot of time for this, but hopefully, I've spent hours looking at this. I think it's fascinating, and so I kind of tend to do that. If we just wanted to look at Greenland and Antarctica, here's what the data looks like. That Grace comes up with. So it comes up with these. It has a funny calendar, so it's in decimals. So 2002.3. So I guess that would be, a third of the way through the year. And then it gives it, it gives it in gigatons. But this is it's a change, so you get kind of this change in ice mass. And just to contextualize, here's sort of an example of a gigaton. And I'm from New York City, and so we like the Empire State Building. And so basically, that's 1 gigaton of ice. And so what I'm going to do, I'm going to pop another URL for you, and that's going to give you access to this graphing tool. And I'll introduce that to you really quickly here. So when you go in, you have a few controls. So you'll come to something that looks like this. You can turn off Antarctica if you want. You can turn off Greenland if you want. And you can also zero in on different dates by moving these sliders down here. Or just kind of like pick a 4-year cycle and kind of move through. And down here, and so this is important. This is actually, you can get graphs that are similar to this on the NASA site. But what we've added to that down here is, depending on what's depicted in this blue bar up here, you actually get the linear regression. And so if you remember your y equals mx plus b, so this number right here is going to be your slope. So that's going to be your rate of change. And so that's kind of what you might want to focus on over the course of the whole data set. So look at Greenland, look at Antarctica. As you click each one, the graph below shows up with the equation for the line. And so what I'd like you to do, and I'll give you about 7 minutes to do this. And don't, if you're having trouble sharing your screen, just do it on your own and kind of maybe have a conversation with people, because I think it's important for you to kind of, okay. And so my instructions for you, this would be like a 45-minute activity if we were sitting in a professional learning room. So don't worry. But basically, your job is to make some graphs. So produce some graphs and just use the tool, and they're made for you. Look at the trends, look at the magnitude of the trends, and then think about the observations that you can make based on this. And also kind of what other questions can we look at sort of with this tool based on this information. I will put the URL for this in the chat. So you might want to grab that before you go into your groups. And so let's unfortunately, this is going to be rather quick. So we'll do 6 minutes until 4:45 Eastern, and then we'll come back and we can have 10 minutes to kind of wrap up and talk about other, questions and other issues. Okay. So give you 6 minutes.
David, I have a question that just came up in our group. So
Sure.
we were looking at as much time range as we could and then comparing Greenland and Antarctica. And we noticed that the rate of change, the ice mass loss is faster in Greenland consistently. Can you say a few words about why that is?
And there's a couple things. One, it's a little hard sometimes to compare Greenland and Antarctica because Antarctica is way bigger. And actually there's places in Antarctica, depending on which side of like that Antarctic mountain range you're on, because there's more moisture in the atmosphere right now, there's actually some places that are gaining snow mass. So it's kind of tricky. And Antarctica is actually, a little bit, it's not as quite, it's a little farther away from the pole. So it probably has like, the warming is going to be more extreme there.
Greenland is, you mean?
Yeah.
Okay.
Yeah.
Thanks.
So that was going to be my questions. Like, what did you all notice? That was one of them. The Greenland seems to be losing ice faster than Antarctica is. Anything else? I mean, they're both losing ice. So
One of the things that came up in our breakout room was comparing those windows of time. And as you look from a 2-year to a 4-year to a all the data perspective, it really changes the storyline. It changes the slope of that line and how dramatic the changes in water storage are. So it just emphasizes the need for these long-term data sets.
right, and then that's really important because even in this area, every year is not the same, and so there's an overall trend, but then there's weather. And so one of the things that we usually do, and I'm going to kind of cut to the chase here really quickly because we're running out of time, is we ask the question: is the ice mass loss accelerating in either of these places? And so sort of there's a crude way to do this that I'll share with you that we've kind of done, that actually some teachers devised, and they just like broke it up into chunks. So this is Greenland, right? So they decided, we're going to look at like these 3-year chunks and from the beginning of the data set and afterwards. And if you look at Greenland, you're like, oh man, it's, at least, using this crude analysis, it looks like the ice mass loss is accelerating. When you do the same analysis for Antarctica, it's not quite as clear. But this was actually a question that during the early days of GRACE, so this paper came out. This is a paper by a scientist named Isabella Villacomia. And this paper came out, I think, in 2009. Yeah, 2009. And she basically graphed the data and decided that it wasn't linear. It was, the best fit line is actually quadratic, sloping downward. And so to her, that was an indication that the ice mass loss is accelerating even over that 7-year time period. And if you want to look at that, if your kids have the ability, if you go into this, and you click on the hamburger here. So this is back to the graph where you guys were at. You can click on this little hamburger and you can download the data and stick it in a spreadsheet if you or your kids or both have the ability to do that kind of analysis. So it's there for you. The place where this data came from, so this is the NASA website where this came from, and you notice there's a break here. So theirs is more up to date. We have to get on this one and add the latest data. But you can tell that the trend basically is continuing. And if you have to register, but you can download this data as well from NASA. if you wanted to do it that way. So there's Antarctica and there's Greenland. But the story is kind of continuing with the Grace follow-on mission. Yeah, that's basically it. Grab my email. And we got a couple minutes we can spend on questions.
There were a couple of questions that popped into the chat box. One of them you've already answered, and that was about how to get the actual data. There was a question earlier from Michelle, who teaches K-5, and she was wondering if the NGSS details are student-facing anywhere. She likes to share all of those details with her students.
Well, and to clarify, I teach future K-5 teachers.
Oh, thank you. Thanks for clarifying that. I misread yours. All right. So the question is, are those NGSS details student-facing?
What are you mean the?
Like you were mentioning the cross-cutting concept and the science and engineering practices. I try to help my students think about science standards as 3D and walk them through those connections, because that's usually new to them and they're going to teach later.
Right. So I still don't quite understand your question, because I think we have to make it student facing, right? There isn't a performance expectation that kind of just incorporates all three. So I would do something like analyze and interpret data to show the effect of human activity on ice mass loss, or the change of ice mass loss based on human activity, to sort of incorporate those three dimensions that I mentioned. So the DCI, like I said, is in the ESS 3, really 3D, that Earth and human activity. And then it could, for younger kids, it might be just, they might want to focus on patterns instead of like this idea of stability and change, but it may just be recognizing the patterns in the data that they see. And you might not want to go to the graphs with those teachers, and maybe just use, although, anomalies is a tough concept for little kids, but maybe just the changing colors of that first graph would be kind of where you would want to focus there. All
right, thanks.
That's challenging.
Yeah, I'm not thinking about having it be student facing for the K-5 students. It's more for my students that I'm teaching, so that they wrap their heads around it. But I think those are how I could structure an activity, for sure.
Any other questions?
Paula, did you want to unmute and ask your question?
Sure. So I was wondering whether there were also any images of the changes in either Greenland and or physically that one could put, or Antarctica, that one could put in image J, because I use that with ozone images and then have them create the graphs from that. So here one could grab the data and give the students and have them make the graphs and see what it told them. But I wondered if there was also the piece that allows them to see the shrinkage in any way in the ice masses.
I've never tried to do that, but I wonder, and I don't know this for sure, I wonder if there's NASA satellites that take, or NOAA satellites that take pictures of Greenland in particular, that you could string together and do that. So that's an interesting question.
All right, can look for them, that's all.
Yeah, and I wonder what you would notice though, because it's not like the ice mass is shrinking visibly this way. It's mostly, kind of shrinking from the top down. So
no, of course, that makes sense. The usefulness of it is that you can animate them and they can see the small changes, which can be measured. That's how it works with the ozone images. So I was just thinking this would be an interesting assignment that would be similar, but with different material.
That would be cool. If you figure it out, please share it.
Absolutely. The image J assignment is a circ exercise, hidden somewhere, buried somewhere. That's where I got it from.
Excellent. So I think I have to stop right there. So I'll turn it back over to Ida, and thank you very much. And make sure you guys, so I'm D. Randall at AMNH, American Museum of Natural History.org. So if you have any questions, you know, shoot me an email. I'm happy to help you out as much as I can.
Okay, I'm going to
Put my email in the chat right now too, since the slide's down. So
I'm going to share my screen real quickly here.
Thank you so much, David.
you're quite welcome.
Ada too.
Okay, are you guys seeing my screen now?
Yep.
Yes.
Okay, I want to make sure that everyone has an opportunity to fill out our post-webinar survey. This is very important information for us, so please do jump on for this link. Mitchell, if you could drop that link into the chat box, that would be wonderful. I appreciate that a lot. Thank you. And then just to give you a quick reminder, the 3 organizations that sponsor this webinar series, NAGT, National Association of Geoscience Teachers, which does have a full set of webinars, not just ours, but others. And the link is in the center of this page. And I'm sure Mitchell's going to drop that into the chat box as well. So please do check out the NAGT webinar series. And we'd love to have you come join us. We are a really fun group in the NAGT community with lots of great resources and benefits for our members. And then also the National Association of Earth Science Teachers invite you to visit NESTA at, I think that should be nestanet, nestanet.org. And the third sponsor of the webinar series in the working group is the American Geosciences Institute. And I invite you to visit their pages for lots of resources and especially Earth Science Week materials. So thank you very much for joining us today. February 11th, again, there will be a webinar entitled Soil Biology, Chemistry, Physics, Oh My. That registration will open up and information will be coming to your inboxes soon. And visit the AGI YouTube channel for our complete playlist. And if you'd like to get in touch with any of the 3 of us, please reach out to us at one of our email addresses. So thanks very much to everybody for joining us today. Thank you, Dave Randall, for a wonderful presentation and engaging us so well in the breakout groups. That was really fun. So thanks very much. And I hope everyone has a great rest of your afternoon.
You're welcome. So everybody, make sure you check out the readings. So go in and check out the readings. And there's actually more of that video that I showed you too, if you want to look at some groundwater issues. So.
Thanks, everybody.